Alright, okay. Sige, 8 o'clock na. Okay, good morning everyone and welcome once again for our PAASE webinars. So this is the 19th webinar that we're conducting this year. And for today's talk, our speaker is a professor of the National Institute of Physics at the University of the Philippines. He obtained his PhD in physics at the University of the Philippines, Diliman in 2004. Before taking a postdoc positions at the Institute of Molecular Science and at the Institute of Laser Engineering, Osaka University. After a stint as a Japan Society for the Promotion of Science postdoctoral fellow in Osaka University from 2008 to 2010, he transferred to the University of Fukui as a specially appointed assistant professor. Through the long-term Balik Scientist Award of the DOST, he returned to the Philippines in the mid-2012 to join the faculty of UP Diliman. He was since put up a modest Terahertz Optoelectronics and Spectroscopy Laboratory at NIP, where he works with his colleagues and students on MBE-grown semiconductor materials and devices, with the primary goal of fabricating more intense terahertz semiconductor antenna sources and more sensitive terahertz antenna detectors. He is also interested in semiconductor lasers and has worked with Professor C. Chang Hasnain of UC Berkeley on MEMS tunable vertical cavity surface emitting lasers for DWDM applications under the auspices of the CHED Picari program. His research interests include terahertz time domain spectroscopy, ultrafast optical processes, and semiconductor optics. He is a member of the Japan Society of Applied Physics and is currently the second vice president of the Samahang Pisika ng Pilipinas. Let us all welcome Professor Elmer Estacio.
Good morning. Ang haba nung ginawa ng mga estudyante. Alright. Pwede na ako magsalita, ma'am? Ay, magsimula?
Yes, you may. And yeah.
Alright. So, good morning, everyone. I'm glad you could come. It's 8 a.m. in the Philippines, kung saang time zone man kayo. Good morning, good evening, good day. So, I'll be, today I'll be talking about generation of pulsed terahertz radiation in semiconductor materials and antenna devices using ultrafast laser excitation theory and applications. This work is done primarily at the Condensed Matter Physics Lab of the National Institute of Physics in UP Diliman. Although I work with collaborators from National Sun Yat-sen University and the University of Fukui, as well as Osaka University, and sometimes in Riken. So for those of the audience who are quite familiar with UP Diliman, this is an aerial view, an oblique aerial view of what was captured by a camera of the entire campus. And this building here is your administration building. The National Institute of Physics, which is located within the National Science Complex, is located way at the back. Yung mga physicists nilagay nila sa bandang likod. Ayaw nilang nasa harap. If we take a closer view, I apologize, this is a rather old picture. This is the National Science Complex of the University of the Philippines, Diliman, and the National Institute of Physics building during this time, probably this was taken around 20 years ago, was still under construction, and this is this building, which is very, very near the intersection of Katipunan Road and CP Garcia. This is the National Institute of Physics building as it stands now. And unfortunately, we have a pandemic going on, but normally I would say you're always welcome to come here and visit our laboratories. We have 6 different experimental and theoretical physics laboratories right now, housed at the National Institute of Physics. And after all these things is over, sana po makadalaw kayo. So let me start by giving an introduction of what terahertz light is. This picture that I show here is pretty much familiar to everyone. This is the visible spectrum of the electromagnetic radiation, and this is the range of colors or the range of wavelengths that our eyes are sensitive to, from very near the ultraviolet, the shortest wavelengths that our eyes can see, and down to the near infrared, around 700 nanometers, a little bit over 700 nanometers, the red region, and these are both ends of the frequency spectrum or the wavelength spectrum that our eyes are sensitive to. However, the entire electromagnetic spectrum is much, much wider than what we know or what we see with our naked eyes. If this is the visible region, we know that it extends towards the high frequency or low wavelength, short wavelength, high frequency, high energy region down to the X-rays and gamma rays. And on the other side, you have your longer wavelength, VHF, UHF, SHF, EHF, and they belong to the microwave region. In this region, you have pretty much a widely developed array of applications. You have your radio communication technology, your microwave ovens, your cell phones, radar systems. And on the right-hand side, we know that this is a pretty much developed aspect of technology as well. We have your microscopy over here, you have X-ray imaging, you have gamma ray imaging, you have applications in medical astrophysics, optical communications. However, between this electronics region and the photonics region of the electromagnetic spectrum, you have a gap here, which we call the terahertz region, wherein not so much development has occurred these past few decades, but we're trying to get there. Technology Review of MIT way back in 2004 selected terahertz as one of the 10 emerging technologies that will change the world at that time. So just for comparison, the terahertz region consists of electromagnetic radiation having wavelengths ranging from 3 millimeters, that's pretty much large, down to around 30 microns. And the corresponding frequency region is about 0.1 terahertz to about 10 terahertz in frequencies. So these are very nice pictures of how we may be able to utilize terahertz light. It can penetrate through clothing and be able to show us concealed weapons, such as this one. These are terahertz images of a man having concealed firearms in his at the back of his at the back of his waist and in his hip. And these are terahertz images of biological samples, wherein the terahertz image is able to see beneath subsurface of what it would be normally invisible to visible light. Lastly, it can also be used as a tool to do fingerprint spectroscopy of complex molecules. In this diagram here, we show the terahertz absorption spectra of a complex molecule showing some signature absorption lines that would otherwise be impossible to detect using optical wavelength spectroscopy or even FTIR. So a more complete array of terahertz technology and its applications is presented in the slides. Terahertz light can be used for law enforcement, medical imaging, as it can see through polymers and is very, very sensitive to the presence of metal. It can be used as a semiconductor processing tool in pharmaceuticals, in agriculture as well, where its sensitivity to water can be exploited to see through corn kernels. And it can also be used in material science applications. So why then is terahertz light, which has been technically proven to be very, very useful, has not been commercialized and developed even at this time? The main problem is that there is a need for intense terahertz light sources. For those of us who are quite familiar with black body radiation, this is the natural emission of electromagnetic waves that a body that has a finite temperature has. So if the body has a low temperature, it would be emitting electromagnetic radiation at this region. If it becomes hotter, it accesses the shorter wavelengths, and much, much hotter, you would be able to see visible light. Pretty much what your incandescent lamps do, or the lamps that you use in your projectors. Not the LED ones, but the incandescent lamps that we use. However, if you take a look at this image, even if you change the temperature from 77 Kelvin up to a very, very high temperature of 700 Kelvin, there is not much increase for light in the terahertz region. And so there is a problem in realizing intense terahertz light sources. In fact, even in device technology, you would have your diodes, high emitting, high intensity impacts or impact ionization transient threshold diodes and gun diodes emitting uh, microwave radiation, and you would have quantum cascade lasers and your semiconductors lasers emitting light very, very intense down to about 1 watt, up to about 1 watt in optical power in the near infrared wavelengths. In this region, in the terahertz region, we have what we call a terahertz gap, which there is just simply an absence of practical light sources. So this was the main, and this is still the main obstacle in being able to fully develop and commercialize terahertz photonics. So before we move on, I would just like to segue for a bit and give a short introduction on how we are able to generate terahertz waves in semiconductors. So this is a typical raw data that we get when we generate terahertz waves in a semiconductor surface. The one on the left is the time domain data of the electromagnetic radiation in the terahertz region. And if we do perform a mathematical process that we call Fourier transform, then we are able to get the frequency spectrum. And in general, the frequency range that we are able to generate when we illuminate our semiconductor samples with ultrafast lasers, which we will be discussing in a bit, is typically in the range of about 100 gigahertz, up to about 3.5 or even 3 gigahertz, terahertz. And this 3 terahertz region is quite wide in terms of spectroscopy, and should be very, very useful when you want to do low frequency excitation of your samples for far infrared spectroscopy. And another thing is that the dynamic range that we get is around 6 orders, meaning our signal to noise ratio is about 5 to 6 orders um, good. So let me start by giving an introduction of a semiconductor material. Shown on the left is the energy diagram of isolated atoms. So we know that you have field energy bands with electrons for energy levels that are low, close to the nucleus. And as you go farther away from the nucleus, then these energy levels will be empty. This is quite what we learned from high school physics. However, if these isolated atoms are made to be brought together closer with each other, then these discrete or isolated energy levels become energy bands. And this is the origin of energy bands in solids. In fact, if we take a look at this plot, which shows the interatomic distance as a function of electron energy, then these energy levels, when they become bands, actually overlap. And if we take a close look at this area here, where this is your Bohr radius, the separation or the energy difference between the highest occupied energy level and the lowest unoccupied energy level becomes your band gap. Okay. So we may think of solid materials as being classified into 3 different types: the conductor, the insulator, and the semiconductor. The lowest energy level, the valence band. The lowest occupied energy level is your valence band, and the highest occupied energy level is your valence band, and the lowest unoccupied energy level is your conduction band. And if these 2 energy levels overlap, you have a very, very good conductor, because it will be very easy for you to promote electrons from your valence band and make those electrons conduct and be mobile in the conduction band. And the classic example of this one is your metal, highly conductant. You can easily allow current to pass through them. On the other hand, you have your insulators, where it would require a very, very large energy for you to promote an electron from the valence to the conduction band. And these are your insulator materials. In between these 2, you have your semiconductor, where the conduction band and the valence bands do not necessarily overlap, but it would not take so much energy to be able to excite an electron from this level to that level. Hence, practically, the semiconductor material can be perturbed externally and be able to make it conduct for for appropriate external perturbations. In this case, if a semiconductor material having this energy difference between the valence band and the energy band is made to be hit by some light. In this case, the energy of the light is much, much larger than the band gap of your semiconductor material, then you are able to promote electrons from this level to the excited level. Eventually, this electron would recombine with what you have at the bottom, the hole, what it left behind, and then emit light. But we're not interested in that. Right now, what we're interested in is the promotion of electron from here to the conduction band. So if I am able to promote an electron from this lower energy state to that conduction higher energy state, then I am going to have a separation of charge carriers between a positive charge, a hole, and an electron, a negative charge. And this separated charges we may call a dipole. And in physics, we have what we call a dipole radiation, wherein if I am able to put a detector that can detect electromagnetic radiation at some distance away from these spatially separated charges, then I will be able to detect electromagnetic radiation. How exactly is this calculated? I am not going to bore you with the details, but the electromagnetic radiation is given by this expression, and this is simply the gradient of the scalar potential that is characteristic of the wave equation for the potentials in this case, and this is the time derivative of the vector potential. If we do the proper representation of these potentials and applying this equation to get an expression for the electric field, we see that the electric field, after so much math, would actually just be simply proportional to a current that is time dependent. What I mean to say is that if I promote an electron from this energy level to that energy level, and this is the conduction band, and the electron is allowed to move in this case, then this time dependent current actually generates an electromagnetic radiation, which incidentally falls in the frequency range of the terahertz region. So what I have here is a drawing that illustrates how a terahertz source may be analyzed or may be illustrated. So if I have a short light pulse that I can use, that I can turn on and off at very, very short intervals, then I can induce electrons and holes at the conduction band of electrons at the conduction band of the semiconductor, and I will be able to generate a current that will also be time dependent and would switch off at some time after your optical pulse has disappeared. And as we know, this time dependent current or current density in this case would generate an electromagnetic radiation, and this is proportional to this time derivative. So if I have a switch here, in this case, a very, very fast switch due to an optical pulse, then if I have a semiconductor, a current that is time dependent will be generated, causing the emission of a terahertz radiation. And if you take the derivative of this photocurrent, you get the time waveform of the terahertz field. It's that simple. Ampere and Maxwell actually did this a long, long time ago. However, why is it that the terahertz technology has not been developed until now? The crucial thing here is that this derivative has to be very, very high for you to have measurable electromagnetic radiation. And this time derivative can only be accomplished. They found out that this time derivative can only be made appreciably high if you have a way of turning on and turning off the excitation of the electrons from the valence band to the conduction band in the femtosecond regime. So the ultra-short optical sources that we use in our experiments and in the generation of terahertz radiation were not around until after the late 80s, not commercially available until the 90s, and are not commercially viable and cost-effective until very, very recently. So yun po ang primary reason. So Semiconductors as terahertz sources would just require that you have a population of electrons in the conduction bands and they are allowed to move at some point. This is a general equation that we use in trying to describe how terahertz radiation is generated by mobile electrons in a photoexcited semiconductor material. We call this a drift-diffusion equation. It has three terms. This term is just simply due to the optical excitation. Kapag malakas ang ilaw, then this laser generation rate is high. If this is low, then this is low. It's also very, very small. The diffusion term is just a contribution to the terahertz radiation by simply a gradient in electron density from one region, presumably in this case, the region where the semiconductor is illuminated and the region where semiconductor is not illuminated. And drift term is due to the electrons being under the influence of an electric field and thus undergoing transport. So a terahertz radiation mechanism in a semiconductor may be characterized by drift, wherein here is the energy band diagram of a semiconductor. Electrons may undergo transport due to the electric field. And since in some cases, electrons near the surface would travel to the bulk region at a faster rate because electrons are lighter than the holes that they leave behind, would generate a net current that is depicted here in this cartoon, where the net separation of the electrons and holes would generate, again, this time-dependent current. So right now, we're looking at how electrons move from the surface to the bulk. However, the terahertz generation may be made to be more efficient if we apply a lateral bias on the semiconductor, and instead of just the electrons moving from this surface region to the bulk region, we may force them to move in the lateral region. In this case, we rotate the plume of the terahertz radiation, not in this diagonal direction, but in the forward direction. And this is realized by the fabrication of photoconductive antennas, where simply we deposit metals on the semiconductor surface, and if we apply a bias that will force electrons to move laterally instead of normally with respect to the surface, then we generate more efficient terahertz radiation. So the next few slides, I'm going to introduce terahertz time domain spectroscopy as we use it to generate terahertz radiation. Some examples of how we use terahertz light, not in UP but elsewhere, and a quick rundown of what we do at the National Institute of Physics. So typically, as I showed a while ago, this is a terahertz radiation pulse from a semiconductor, and this is typically seen for sub 100 femtosecond pulse widths, having optical pump powers in the milliwatt range, and this corresponds to a terahertz beam that would have a spectral range of about 3 terahertz, having 6 orders of signal to noise ratio. How do we measure this terahertz pulse in the first place? So what we have here is a schematic diagram of the terahertz time domain setup that we have. This is your ultralight or ultra fast light source, the femtosecond laser, and the light is split into two. We have the pump beam in this side, and we have the probe beam in this side. This pump beam generates the terahertz light using the photoconductive antenna, and this probe beam is fed onto another photoconductive antenna detector where the generated terahertz radiation is focused onto the second antenna, and it is switched by the other half of the ultra-short optical pulse. So if I have this terahertz waveform that is incident on my photoconductive antenna detector, okay, successively varying the time delay or the time it takes for this terahertz pulse to be incident on the photoconductive antenna detector and the optical pulse that switches this antenna at the same time, this time of arrival of the optical pulse here actually slices in time and samples in time the waveform of the terahertz pulse. And if I do this several times, I am able to measure a signal from the photoconductive antenna detector that will be proportional to the time propagation of my terahertz pulse generated by this photoconductive antenna emitter. So this is the actual picture of a photoconductive terahertz time domain spectroscopy setup. Um, Maybe just for comparison, these photoconductive antennas are probably in their holders are probably around 5 or 6 inches in size. Okay. These are the photoconductive antennas that we use. Note just want to show this to give reference of the sizes. The gaps are typically in the order of 5 to 10 microns. And this is your metal region, and this gray area is the semiconductor material. They can have different geometries as well, depending on the frequency range that you want to work on. And if I want to do spectroscopy, it's pretty much the same time domain spectroscopy setup, except that now I make sure that I have enough space here and put some sample. And if this sample is able to transmit terahertz radiation, then I am able to do spectroscopy. So to show you what we mean, say for example, I have this terahertz pulse and it is made incident on some sample with some optical properties and some thickness D, then if I don't have the sample, the terahertz radiation will just pass through. If I have the sample, this terahertz pulse will have some modifications. Either you get some time delay, the signal may be attenuated, and this time delay would correspond to some phase shift, which would give us information to the refractive index of the material. And the attenuation would give us information on terahertz absorption coefficient of whatever material you want to study. So enough of those equations and diagrams that show some nice cool stuff. This is a chocolate bar, and in the factory sometimes you would have to do quality control, and these are um, glass shards and other foreign objects that are embedded subsurface underneath the chocolate bar, and we cannot use microwaves to detect this. We cannot use x-rays, too expensive. Microwaves would just melt the chocolate, and they are able to do subsurface imaging of these chocolate samples using terahertz time domain spectroscopy. And terahertz is very sensitive to water. Right smack here, this is the water vapor content of our um, ambient air, and the terahertz region right smack in the middle of the region where you have very, very high water vapor absorption. And as such, this is a terahertz image of a leaf freshly cut from the tree, from the plant, and this is after 48 hours, showing much dehydration. However, right here, you still have water content. And this is a famous paper by Austin, and this is a more recent paper showing the capability of terahertz light to do subsurface imaging of IC packages without having to remove the polymer um, encapsulation. And since it is very, very opaque to metal, then you can discern uh, failure by looking, being able to look at disconnections in the metal circuits underneath your polymer encapsulation. In the medical field, it can be used to look at subsurface images of cancerous tissue. This is, of course, very, very much experimental at this stage. But due to the fact that, again, terahertz light is very sensitive to water content, and they have shown that cancerous tissue has a different water content than healthy tissue, then what was normally unseen by visible light showed that cancer cells have actually invaded this liver tissue quite extensively underneath. And I would like to play this old movie that our collaborators in Japan did. This is a contraband hidden in a mail envelope. This was done in Osaka University, and they used terahertz wave to, without infringing any privacy and human rights of the mail end users. They're able to see contraband material through the envelope. This is, I think, methamphetamine. that they put inside a mail envelope. So on the commercial aspect, why are we interested in terahertz? The terahertz market is not yet mature, as I was telling you a while ago, but with the compounded annual growth rate that they calculated of 26.8%, and from 2016 to 2024, the market research companies estimate the terahertz market to balloon to about 430 million US dollars by 2024. That is, of course, these forecasts were made before the pandemic. And the market shares are distributed by these companies, would be distributed by these companies. These are companies, US companies producing defense related, military related hardware. Grumman and the Lockheed Martin. Ruger is a scientific equipment laboratory company, and these are your photonics companies. We go back to the present. This is the actual terahertz market at this time. Here's an example of a company, a German company that sells photoconductive antennas that we use as emitters, terahertz emitters and detectors. And they start off with a semiconductor wafer that would cost you around 500 US dollars for each 2-inch wafer. They do the layer growth and they do the molecular beam epitaxy growth and they fabricate the photoconductive antennas. They can probably fabricate about 50 discrete devices from a single 2-inch wafer. The 4-inch wafer becomes 4,000 US dollars in price when you fabricate it into an antenna. You cut off each one of these 30 or so devices, put it in a box, put electrical connections, and suddenly this single wafer becomes 2,000 US dollars times 30. So basically, tubong lugaw po yung negosyo ng photoconductive antennas at this time. That's why we want to be able to try and see if we may be able to join in. Of course, that's in the future back. So how are semiconductor-based photoconductive antennas fabricated in the first place? The low temperature grown gallium arsenide layer on which we fabricate the metals for our photoconductive antennas are actually grown using a molecular beam epitaxy machine that we do have at the National Institute of Physics. We acquired it way back in the mid-1990s, but it was operated only during the early 2000s. And this was acquired through, I'm not sure if you're familiar with ESEP. It was one of the ESEP grants during that time by the World Bank. It was a World Bank loan. And this machine in ultra-high vacuum environment allows for the atomic monolayer by atomic monolayer deposition, epitaxial deposition of semiconductor compounds. In particular, our semiconductor research is based on gallium arsenide, a 357 conductor, which would have a band gap in the near infrared region, around 800 nanometers, pretty much right smack in the middle of the ultra-fast laser light sources that we use for our terahertz research. After the layers are grown in the molecular beam epitaxy machine, we have a mask aligner and a metal deposition facility to fabricate our devices, wherein briefly, if we have our cross-section drawing of a semiconductor here, we grow a photoresist, we spin coat a photoresist, put our mask, metal mask, which covers appropriate areas of our device, illuminate it using UV light, yung tinamaan ng ultraviolet na luluto, and we can easily remove them, okay? Put this thing in the metal deposition chamber, deposit metal on everything. However, metal deposited on the photoresist after chemical immersion is lifted off. And you only get the metal that is on the semiconductor surface itself. And depending on what kind of mask you use, you are able to get and fabricate photoconductive antenna devices. This is a very, very simple device fabrication process. The ones that you have in your semiconductor industries are way more complicated. This is an array of light sources that we have in our laboratory. This is a very old and very reliable titanium sapphire femtosecond laser. This was actually used even by Vince during his time. And we have acquired much more cost-effective. Wala kasi kaming ganun kadaming pera po. Femtosecond light sources based on fiber-based lasers. And I came back and joined the faculty of the University of the Philippines in 2014. And since then, I have devoted my research efforts on pretty much on terahertz science and photonics. And we have been able to publish our works on the development of novel semiconductor materials that may be used as terahertz light sources. And these are publications that we were able to, to, to produce in 2014 and 2015. This will be the basis for the photoconductive antenna devices that we were at that time planning to fabricate in a few years. So these were published in Applied Physics Express and Josephine. Eventually, these students would be getting their PhDs and doing postdocs. At the same time, we are also interested in looking at the interaction of terahertz photons with very, very confined spaces. As you know, a while ago, I said that the terahertz light has a very, very long wavelength. That's why the energy is very low, and that is simply why our eyes cannot see it. It's much, much more invisible, I may say so, than infrared. And the wavelength of terahertz light is within the order of magnitude, a few hundred microns. And if we are able to develop conducting materials or arrays of metals having spacings pretty close to the wavelengths, and we may be able to observe some pseudoplasmonic effects that are normally observed in the microwave or even in the visible region. And we were able to do so. And a few years ago, we were able to demonstrate a strong enhancement of terahertz radiation in semiconductors if we fabricate an array of closely spaced gold lines in a gallium arsenide layer. And we published this work on our terahertz enhancement, emission enhancement in a metal line array in Optics Express. And we also looked at trying to survey other ways of doing gallium arsenide films in the molecular beam epitaxy. A while ago, I mentioned that gallium arsenide wafers cost around 500 to 600 US dollars. It's quite cost effective, but still relatively expensive if you compare it with silicon. Silicon is way cheaper. One wafer would cost about a third or a fourth of the gallium arsenide substrate price. And if we are able to successfully grow gallium arsenide on a much cheaper substrate, and it should bring down the prices of photoconductive antennas. And that's what exactly we did here. First, being able to successfully grow gallium arsenide films on silicon, we were able to show how we are able to generate terahertz radiation using these layers. This was just last year. Of course, we've been working on this for a few years back. And with the advent of with our procurement of some equipment, more modern equipment in device fabrication, we were able to finally develop our own photoconductive antenna devices. And this was a follow-up paper to the gallium arsenide grown on silicon. We were able to successfully fabricate antennas using those substrates, and we were able to show very, very wideband terahertz radiation, having close to 7 orders of magnitude signal to noise ratio over a very wide frequency range of more than 3, almost 4 terahertz. This was published I think just this year, and we were able also to show our capability to grow novel multi-layers of gallium arsenide and be able to show that we can actually further improve the terahertz radiation intensity of our photoconductive antenna devices. And this is very recent. I think this was accepted just during the start of the quarantine period here in the Philippines. And lastly, we went back to the work on trying to look at how terahertz photons can interact with very, very constricted spaces and result in terahertz generation amplification. This was in 2014 into optics letters. And very recently, we were able to show that if instead of a 1D array of metals, we use a 2D structure, then we are able to show that we can generate spherically or circularly polarized terahertz radiation, and in 2 dimensions, not just in 1 dimension. And we were able to show that we can increase the terahertz radiation even up to 2 orders of magnitude in power. This is terahertz radiation spectra for the bare gallium arsenide, and these are for the surfaces wherein we deposited 2-dimensional metal arrays. So actually, this has not come out yet. So winding down, in the abstract that I sent to Ma'am Kathleen, I promised that I would be talking about COVID. I did not promise that I will be talking a lot about COVID-19. I did not promise that I understand COVID-19, but there have been reports that terahertz light may be used to eventually detect the SARS-CoV virus. And terahertz light, in conjunction with metamaterials specialized for detection of molecules that have sizes or dimensions within the range of the coronavirus, may be designed and used so that we can use it as an alternative way to detect this coronavirus infection. So we are not working with COVID-19 coronavirus detection using terahertz light at the moment. So what I'm going to show you is a survey of materials and publications, of recent publications that I was able to see that are related to terahertz light and possibly coronavirus detection. So this is a paper that was published in Biomedical Optics Express in 2017. And by fabricating metamaterials, metals on some substrate, which would have dimensions pretty much within the range of the size of the virus. In this case, they looked at 2 types of viruses, PRD1 and MS2. Please do not ask me what these viruses are. I just know that their sizes, corresponding sizes, are 60 nanometers and 30 nanometers respectively. And your SARS-CoV virus is around 60 to 140 nanometers, if I remember it right, pretty much within the ballpark. So in their experiment, they are able to deposit a solution on this surface wherein they deposited metals having gaps within the range of a few nanometers, a few hundreds of nanometers, down to several microns. And they are able to see some changes in the transmitted terahertz light. And this change in the frequency peak of the transmitted terahertz light, if you put a virus compared with just the metamaterials with no virus present, shows a change in frequency that is sensitive down to 1 virus molecule per square micron. So this is the selling point of this work. They were able to show using a metamaterial, what they call a nanogap metamaterial, show very, very sensitive detection of a virus having dimensions of around 30 nanometers, 60 to 30 nanometers, even with just a very low particle density of one particle per square micron surface density. Because when you drop the solution, it becomes practically a surface, not a volume. So that's one promising thing that I'm looking at. And this is more of a simulation work. It's titled Terahertz Biosensing Metamaterial Absorber for Virus Detection Based on Surface Spoof Plasmon Polaritons, pretty much what we are doing. also doing with our spoof plasmon work. And I can give you the dimensions here. These are in the order of several tens of microns, and they are able to fabricate this pattern here. Looks like a cross with these edges, and deposit it on some substrate, and they allow terahertz beam to be incident in this direction and be transmitted. And if they spray a solution of virus material on the surface, then their calculation shows this is just a simulation work, that several virus types may be identified, not just detected, okay, based on changes in the effective refractive index of this metamaterial system. And they can actually shift the peak transmission of terahertz light and be able to identify these three types of flu viruses in their simulation work. So this is also, this is again, simulation work, but it's also a promising proof that terahertz light may be used to detect coronavirus. So from our side, we have been working on something quite similar. Our work on spoof plasmons in the 1 dimension and the 2 dimensions have been demonstrated to enhance terahertz emission in semiconductor materials by as much as 2 orders. And we are also doing work on further improving the bandwidth. Because the more bandwidth we have, the more chance of being able to capture the fingerprint absorption lines of a biological material. We are able to increase the detection bandwidth of our photoconductive antennas. And of course, we are not going to do this alone. In fact, we are not allowed to do this alone because we do not have a certified biohazard lab. Together with key scientists who are actually experts in coronavirus detection. Sir Al, are you there? Perhaps we can develop a totally in-house terahertz-based detection system. So, sinusubukan po namin gawin yan in as much haste as possible. We are already able to put together a dedicated terahertz CDS system for this work. We are just looking for we are just waiting for the samples to come in collaboration with Sir Al and his team. Hopefully, we'll begin testing in a few weeks, if not in a month. This lockdown has really done so much damage to our research activities. So before I hope Ma'am Giselle is listening, before moving to the last slide, one of the main research collaborations that Dr. Concepcion, VP Concepcion, instigated during her time as Vice President for Academic Affairs in the University of the Philippines system was collaboration ties with the National Sun Yat-sen University, and we were able to establish work with them. The physics department has a very active semiconductor optoelectronics lab, but they're not doing terahertz, so we collaborated with them through the initial contact established with the OVPAA, and we were able to publish 2 papers recently. And Alex de los Reyes, actually got his PhD degree during the pandemic. One of the first few people who at this time did their PhD defense online, not face to face. Unfortunately, my collaborator in National Sun Yat-sen University passed away. I don't know. I haven't asked. I didn't ask which reason, but he passed away just this March. Sayang lang, sayang. So, acknowledgements. Lastly, our work is primarily funded by the UST, PSHERD, and the Grants and Aid Program. We also get funding from the Vice Chancellor's Office of the Vice Chancellor for Research and Development, PICARI, on a different research topic, but we oftentimes would use the molecular beam epitaxy machine and be able to run and fabricate grow some samples that we would use as photoconductive antenna devices using some growth money taken from Bicari. And just would like to acknowledge the Office of the Vice President for Academic Affairs. I came back to UP in 2012 when Ma'am Giselle was the VP for Academic Affairs, and she was the one who spearheaded the Balik PhD program. And the majority of my equipment that I'm using right now, in collaboration with National Sun Yat-sen University, with Japan, publishing and graduating students, were acquired by the funds from the Balik PhD program under the leadership of Ma'am Giselle. So with that, I end my presentation. I hope I didn't go over time at 10 minutes. So I'm ready to answer questions. If you have some.
Okay, thank you very much for that presentation, Elmer. And it was really very interesting. Maybe I'll take a comment from Al since you called him out a while ago.
Malaki yung utang ko sa kanya.
Hi, Al. Are you there?
Yeah,
Okay.
maninigil na ako sa inyo.
Kaya pala siya umattend.
Yes, sir. Operational na yung we're still improving the system, but I have already constructed a dedicated system that will work on what we're going to try and do. If I may, can I send an email again to our collaborator from Los Baños so we can have the samples delivered? I can go to UP Los Baños. If I don't know if I can go there. Hindi naman na yata mahigpit ngayon, ano po?
Tama, I'm talking to BC Rex and College of Science team, soon. But yeah, please feel free to send an email at ano. Actually, she's a referral Giselle from Vic Ilag also. So
ang sabi po sa akin, yes sir. Ang sabi po sa akin, basta 4 degrees C ang i-maintain in transport and in storage, then they should be okay. Would an ice pack do? I don't know. I'll have to talk to her to the details. Sige po.
So it's not really a virus, so technically it should be okay from a biological hazard standpoint.
I see.
But we're looking forward.
Opo.
Kasi marami tayong kompetensya na in terms of detection. I mean, we were just looking at an Illinois development on microarray, 3D printed bio assays that are coming up very quickly. Well, but I still believe in non-biological detection because they've used terahertz in my school in Rensselaer as far back as 10 years ago. I was a jury for a startup company in RPI because I came to our RPI. One of the ones that we approved or won of that year was a handheld scanning device for using terahertz for explosives. So I'm looking forward to us having a handheld device just scanning somebody for COVID, even for saliva applications as well. So yeah, please do send and follow up, and I will also tell the bosses in UPLB that this is something that we want to do inter-CU in very soon. Thank you, Elmer, for mentioning.
Thank you.
Okay, I think Vince has a question.
Yeah, I have several questions. So you're using gallium arsenide, and these are direct band gaps, is it?
Right.
So when you excite them with a femtosecond laser, you put the electrons transfer the electrons from valence band to conduction band. Would it transmit? Would it radiate the standard energy that it's supposed to emit, like near infrared, for example?
Yes.
Once you do that at the same time?
That's right. So shown here in this slide is the energy band diagram of a direct gap semiconductor. We can think of this as gallium arsenide.
once you excite it with the femtosecond laser, you get motion of the electrons, and then once the electrons goes back, then they will emit the standard energy level that it should be emitting.
Right.
Aside from the terahertz.
That's right.
Is that correct?
Yes, Vince. once you optically excite the semiconductor material, and you are able to promote electrons from the valence band to the conduction band, then the progression of events will occur.
Okay, so you
And
have
the
two lights. You have
luminescence,
terahertz light and you have near infrared
right.
light.
So what you're talking about, the excitation or the luminescence. If the electron that is promoted to the conduction band eventually gets in touch with the hole it left behind, and they recombine and they produce light, and that's what you call your luminescence.
Okay.
It happens. I cannot prevent that, but I cannot detect that.
So you're just filtering that away.
I actually do not need to filter. I cannot detect it. The antennas are not sensitive to luminescence.
All right. Okay.
And,
the second question. Yeah.
All right. Okay.
No, that's clear. So the second question is that I realized that your spectrum for the metal array, one with the metal array, is is less than 1 terahertz frequency.
That's right. That's right.
It's very thin.
Thank you for pointing that out.
Is that correct?
Okay.
Most of the spectrum is broad, like
That's
3
right.
terahertz. And actually, I don't understand what do you mean by 0 frequency there in your spectral plots.
It doesn't mean anything. It's a plotting error, if I may say so.
So what do you mean by
there is no 0.
No.
This is a mathematical artifact of the Fourier transform. So please excuse that.
I mean, there's no such thing as
right,
0 frequency.
That's right. No, there's no such thing. This is a Fourier transform error and plotting carelessness. But people who do terahertz work actually do this, and we get away with it. But terahertz radiation coming from these types of photoconductive antennas would typically have a lower frequency limit of about 250 to 300 gigahertz. Around here. And regarding the bandwidth question, yes, that's right. The bandwidth of the terahertz radiation coming from this kind of structure is much less. Number one, please note that the thickness of the gallium arsenide substrates that we use here is much thicker than the photoconductive antenna devices that we use for the substrates that we use for the photoconductive antennas, about half. And number two, these antennas are electrically biased, and the electrons are forced to undergo lateral transport at a much higher distribution of velocities. So the effective frequency range that you get from this higher velocity transport is wider. And in this case, you're just relying.
When you transform that to wavelength, that will be a broader wavelength. Is that correct?
If the velocity is smaller, if they are moving at a much slower velocity, then you get lower frequency spins. You suffer in terms of bandwidth, actually. So it's a drawback of this.
The opposite. So I mean, anyway, I'll just ask that question. Well, would it be possible to use to make a terahertz laser, for example? I mean, if you have a broader frequency spectrum,
that's right.
Would you be able to produce a very fine terahertz laser?
They have. In fact, it has been experimentally demonstrated already. Yes. What they do is generate terahertz light and then put an external cavity, and they are able to select frequencies. But they do this using high energy lasers, laser amplifiers, and crystals, nonlinear crystals that would exploit difference frequency generation to get the low frequency excitation in these nonlinear crystals. This kind of terahertz radiation has probably, if I may say so, a very low conversion efficiency compared with nonlinear optical effects that may be used to generate high intensity broadband radiation that you can actually, what you're saying, put in a cavity and select wavelengths for amplification. In practically a laser.
All right, thank you.
Thanks, Vince.
Okay, thanks for that, Vince. Any other questions from our audience? Okay, maybe I'd like to ask, most of the things that you've presented, Elmer, were based from gallium arsenide. Are you
Yes, ma'am.
exploring um, other potential candidates? Um,
Yes. Thanks, Amkat. The reason why we're doing gallium arsenide is that our MBE is tailored for pretty
mm,
much gallium arsenide based materials. In fact, we can also do ternary alloys, indium gallium arsenide, aluminum gallium arsenide, or even indium gallium aluminum arsenide. These things that you play around with, but pretty much based on gallium arsenide. And that is an instrument limitation. However, if we take a look at this plot, the most intense terahertz radiation that was observed for semiconductors illuminated by short pulse laser pulses is indium arsenide, which we may also be able to work on. But since there's a very, very big drawback when you use indium arsenide, it's not transparent to terahertz, and everything has to be done in reflection geometry. It becomes very, very tedious and quite complicated um, in terms of implementing this, using this device, this material, implemented in a device and use it for actual laboratory work. So indium arsenide is this one, and gallium arsenide is actually just a fourth of the intensity, but it's not very practical. We're also, there's a group that's doing the physics on how indium arsenide quantum dots generate radiation, and that's what we're working with the National Sun Yat-sen University was with. But in terms of fabricating commercially viable antennas, we would like to focus, at least at the moment, on gallium arsenide now. Thank you.
so the materials that you use, correct, are being fabricated in your lab. Is that correct?
Yes, ma'am. All in house. Of course, the sources, the gallium, the arsenic,
Oh,
are
yeah, yeah.
sourced outside, but everything is done. Otherwise, everything is done in house.
Okay, so I'm not so familiar with the semiconductors, so I just want to ask, like, how much different is it with semiconductors that you would see commercially available?
Okay, a good question actually. Pretty much the gallium, the semiconductor industry and the whole um, technology and the industry that goes with it, commercialization and all, is based on silicon.
Hmm.
Gallium arsenide at this time is still quite expensive compared with silicon if you want to scale device application from low level integrated ICs to high level memory devices. If you use gallium arsenide for that, you are going to have much faster devices. However, our infrastructure is not yet suited
All
for
right.
gallium arsenide technology. So they're quite different in terms of material aspect now. That's why we're doing the opposite. We're trying to use silicon instead, because that's
Oh,
cheaper.
okay. Okay, thank you. Thank you. It was really a very interesting presentation. So, any more questions from our audience? Okay, I think that's it.
Thank
Elmer,
you.
do
Thank
you
you
have
very much, ma'am.
any final words for our audience?
Wala lang. Magandang araw sa lahat. Thank you for having me. Thank
Oh,
you for having me.
yes, yes. I know that you're one of the most productive researchers in UP.
Hmm.
Um, yes, you are. I'm sure you are. And then what's this? Oh, some of the people who has joined us to here are asking if they can get a copy of the presentation.
Yes, sure, sure.
Yeah. Okay. So if you can just send it to me, even in
I'll
PDF.
send the PDF, ma'am.
Yeah, and then I
I
can.
don't have animations here anyway, so
Yeah, and
couldn't
then
have.
I can disseminate it to.
Can I send to you by email na lang po?
Yes, 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 yes,
Okay. All right.
yes,
Hey,
yes.
thank you, Elmer. I'm here not to
Thank you very
stop,
much, Edsel, and
but
thank you for
just
staying.
yeah, just make sure that you don't tell Trump, the president here, about the possibility of using this terahertz technology to detect COVID-19. Otherwise, you might be in the news and it will destroy your research.
If we somehow let him ingest gallium arsenide, then that would be good.
I'm joking.
Thank you very much po, sir.
Thank you.
Okay, before we close the session, I just want to share with everyone our next session.
Sorry, I'll stop sharing.
It's okay. Okay, can you guys see my PowerPoint now?
Yes.
Yeah.
All right, thanks. All right, so thank you very much, Professor Elmer, for that very interesting presentation. And we look forward to the developments of this work, of your work. And yeah, hoping to see that development with Al Serafica as well. So next meeting, we will have Professor Edsel Peña. He will talk about knowledge updating, decision making, and the search for truth through data. So we'll have it again on a Friday, 8 o'clock in the morning for those of us in the Philippines, but 8 p.m. Thursday night for those of you in the US. So those interested, kindly register at bit.ly/edselpeña. Okay, let me promote another one. So this was emailed recently by Dr. Joel Coelho. So after Professor Edsel, we will have Dr. Cherry Murray to speak about UN Sustainable Development Goals and the pandemic. So registration for that is also already open, but she'll be talking on September 25, which is the Friday after next week. Okay, so everyone, you can find us on Facebook at our Philippine American Academy of Science and Engineering official page and our website, which is paase.org. And the webinars that we're conducting, we try to record everything and upload them at Paase Webinars, bit.ly/Paase Webinars. Okay,
And
so
thank you very much,
that's...
Kay, for organizing this.
Yes, March, maybe we can have you next time also. Yay!
No, actually, this is just one of our new members who has a lot of work on environmental.
Yes,
So
please.
I'll email you. Yeah.
Yes, please.
Okay.
Okay. Thank you, thank you. So that's it. Thank you very much, everyone. Thank you very
Salamat
Thank
much,
po.
you,
Maraming
guys.
salamat.
Salamat. And I
Nice
hope to
seeing
see you guys
everybody.
next week.
Yeah.
Thank you po. Salamat po. Thanks, Elmer. Good job.
Thank you po. Mag-leave na ako. Okay na mag-leave na.
Yes, yes, yes.